Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
All right, so we're very happy to have David, who's been visiting us for off and on for a whole year almost, and finally we managed to get a Wednesday during which we were free and he was free, and so he's going to tell us about Primal-Dual Approximation algorithms, which is a topic, of course, he's very familiar with.
Great, thank you, Madhu, and I want to take this opportunity to thank Microsoft as a whole because it really was a fabulous year, and my Thursdays were really the high point of my week. So, I'll be talking today about strong LP formulations in Primal-Dual Approximation algorithms. And this is really the union of pieces of two papers, one joint with one student, Tim Carnes, who's currently a postdoc at the Sloan School, and Maurice Cheung, who's still a PhD student at Cornell. Though he's still, well, not almost still physically here. So what am I going to talk about in broad picture? So if you think about the standard approach to solve combinatorial integer programs in practice, then the methodology that is dominant in practice is to start with a relatively simple formulation for the problem, and then to gradually add so-called cutting planes or additional valid inequalities so as to tighten up the relaxation, so as to drive a branch and cut philosophy for the design for getting good integer programming solutions. And what I really have been interested in for quite some time is to think about how we can get alignment with that way of thinking from the empirical side to the theoretical side. So we want to take simple combinatorial optimization problems for which the first natural LP formulation, relaxation, doesn't generate good bounds, and think about classes of valid inequalities that we can add so as to get better bounds and be able to prove strong approximation results. So that's the framework. Oops, I shouldn't have done that. And the terminology, I'm sure you're all familiar with, but just to say it once, that when I talk about an alpha approximation algorithm, I'm talking about an algorithm that runs in polynomial time and finds a solution of cost within a factor of alpha of the optimal cost. Okay. So what I'm going to talk about, I'm going to talk about the Primal-Dual method, which is a well-known leading approach for the design of approximation algorithms for NP-hard problems. And I'm going to focus on a small handful of so-called capacitated covering problems, in particular two examples, the so-called covering knapsack problem, and I'll define all these things later, and a single machine scheduling problem. And in fact, one curiosity for someone who's thought about problems in this space before is one tends not to think about scheduling problems as covering problems. They actually tend to be more like packing problems. And we'll see how, in fact, we can sort of straddle those worlds in an interesting way. And I'm going to give constant approximation algorithms based on enhanced linear programming formulations. So if we think about approximation algorithms in linear programming, why is it such a useful tool? Well, for one thing, it's very easy for your optimization problem of choice to set up an integer programming formulation. We can consider the linear programming relaxation. Linear programming is solvable in polynomial time. We can get an optimal solution, and then we can use the optimal fractional solution so as to generate a good integer one. If the quality of the solution doesn't degrade too much as far as the rounding procedure, let's say it gets a factor of alpha worse, along the way we've also proved a factor of alpha in terms of the performance guarantee for the original integer programming problem. The key and the underlying thing always in using an LP-based approach is to start with the right LP. And really that's sort of the theme that's recurred over the last 25 years, that if you get the right LP, life becomes so much easier. And of course, I'm focusing on linear programming, but of course, there's been work extending that to things like semi-definite programming and stronger other solvable convex programming relaxations. So the LP-based approximation algorithm has, or any math programming-based approximation algorithm has the additional advantage in practice that you don't just get a theorem that you've proved up front, but for each input that you consider, that you have how close it was on that particular input, because you may have a much stronger bound, and the LP gives you the bound for that input, and you know what you did relative to the rounding procedure. And again, so the goal is to try to provide a theory for why, at least some examples of cases where the addition of additional valid inequalities gives us stronger and provably good LPs. However, while I just talked about linear programming in the context of solving the fractional solution and rounding, in order to provide, take advantage of this philosophy, we don't even need to solve the LP, and we can take advantage of the mathematical theory of duality of linear programs and mathematical programs in general. If I'm focusing on linear programming, if I think about a minimization linear program, every minimization linear program has a dual maximization linear program. At optimality, they're equal. And by virtue of that, any feasible solution for one provides a bound on the optimal solution for the other. So on the one hand, I can design now an approximation algorithm with provably good performance if I hand you both a good integer solution, let's say for a minimization problem, and a good feasible solution for the dual. If I show that they're within a factor of, let's say, alpha of each other, then I know that I have an alpha approximation algorithm. If I show that the algorithm always has that, that's going to be the design philosophy. And that, we can use the usual chain of inequalities, that if I think about the integer optimum, that's always lower bounded. Again, I'm thinking about a minimization problem by the LP, that the dual provides an optimum. And this is what I'm going to try to prove for every algorithm. I'm going to prove a given algorithm. I'm trying to show that the cost of the solution that I construct is within an alpha factor of the dual solution that I'm producing. And by doing that, then I just rip up to the right, and I know I have an alpha approximation algorithm. Okay? So by merely proving that if I have an integer solution and I always generate a dual solution that's within a factor of alpha of each other, I'm done. Okay? And that's going to be the design paradigm. So again, I'm now going to do this in the context of adding valid inequalities. I'm going to be thinking about starting with an LP formulation, which the first cut is going to be weak. Formally, when I think about that weak, I think about the worst case performance of what's the optimum integer solution over the optimum LP solution. We're going to show a very simple, even trivial case where that's unbounded. And then I'm going to show how we can fix that up. Okay? And we're going to do that by adding additional inequalities. And in fact, the inequalities that I'm going to focus on throughout all the pieces of this talk are a family of inequalities known as knapsack cover inequalities. In this particular form, they were introduced in a paper dating back more than 10 years of Carr, Fleischer, Leung, and Phillips. And they exploited these inequalities in the context of rounding algorithms. So they solved an exponentially large LP more or less with the ellipsoid method, and this was further complicated by the fact that in order to think about the philosophy of adding valid inequalities, one of the engines you usually need is the ability to, given a solution, detect whether one of them is violated and generate those inequalities on the fly. And that in particular for these, that wasn't known, but they had a number of workarounds. There are two different approaches they could do. But they obtained nice results out of these knapsack inequalities in the rounding perspective. And one of the things that we set out to do, and I'll show you in a very simple way, is to generate a primal dual analog of their kinds of results, first starting with some simple models and then going on to more sophisticated ones. So I'm going to talk about a number of results. This was one of the slides that was created between now and 1 o'clock that got deleted when it crashed. Okay, I had a machine crash that I lost everything between 1 and 5. So I think I did the repair, but I just discovered one. So I'm going to talk about, in particular, and these were highlighted in red in the updated version, a problem which I'll call the min-cost covering knapsack. And I'll focus on two single machine scheduling problems, one of minimizing the weight of late jobs and a general min-sum scheduling problem. But there are a whole host of other examples for which we can apply the same philosophy and get a Primal-Dual 2 approximation algorithm. So one of the things I talked about up front, and this is sort of really where some of the most recent work initiated from, is in what I'll call a minimum sum one machine scheduling problem. And this is a very general framework, so let me just walk you through the notation. So I have a single machine, and I have a collection of jobs. Let's say n jobs. Each of them has a processing time. I can only schedule one job at a time, but that's the limit of the constraints. And now I have a cost function for each job. Each job has its own personal cost function, which is a non-decreasing function of its completion time. So depending on when it completes, I have some cost, but the only restriction that I'll make is that it be non-negative and that it be non-decreasing. Okay, so those are, and now the goal is order the jobs, and indeed it's really just a question of constructing and ordering, because there's no point in putting any idle time, because that only makes the cost of anything worse. Order the job so as to minimize the total cost. Okay, now, in spite of the fact that there's been a tremendous amount of work on approximation for scheduling and that, I must say, the number of times I've said, okay, I'm done doing approximation algorithms for scheduling problems, I won't even want to count. But nonetheless, one thing that was really observed over the last couple of years and highlighted by a paper by Bansal and Pruhs is not very much known about when you go up to this level of generality. In fact, Bansal and Pruhs gave the first constant factor approximation algorithm for this problem, something like 16. They didn't worry particularly about what the absolute constant was. And more to the point, they talked about another variant where let's add a minimal level of additional constraint. Let's add that I have release dates on the job. What does that mean? It means I give you a time for each job, and I tell you I can't start that job before then. Okay? And now, well, if I just give you that, I get a really hard problem in terms of trying to, I can prove that you can't have any reasonable approximation. Let's relax the problem a bit. Let's allow a common flexibility in scheduling, so-called preemption. I can stop one job, start another job, and pick up on that job later. And that sort of fights the tension of the fact that we have these release dates, because something that has, is much more urgent and gets explosively more expensive all of a sudden shows up, and you have to sort of take advantage of that. And Bansal and Pruhs gave a log-log NP approximation. P is the total processing time in the system. And I figured I'll front load the open questions because people are usually exhausted by the end. So I'll sort of pose one question that we did not resolve is there a constant approximation algorithm for this model? Okay. So and I strongly believe there should be. And
F sub j is how are they given?
So I understand that once I give him, I'm going to have to sort of deal with the complexity of the specification. I'm just going to assume I have I have a polynomial size circuit and it's specified. It's really not going to be important. Very general. I mean, as far as being able to compute, let's say, their constant approximation algorithm, all I just need is a polynomial time function. It's just okay. Oh yes. So. Maybe that'll be later, but it's strongly NP hard, even if I just want to minimize the total weight of the so-called tardiness of the job, so how much beyond the specified due date is it, and I just have some weighted average of those tardinesses, that's already strongly NP hard. So very, very simple.
Do you know whether it is okay
No, I don't. And next slide. 10 seconds. Okay, so you took away my ability to do my self-promotion. So David Williams and I just finished and just appeared a book on approximation algorithms, and we felt, in some sense, morally compelled that as a last chapter, we should think about what are our top 10 issues. And in roughly speaking, as we were sort of thinking about and debating amongst ourselves what problems to include, problems came into a number of different flavors. So there were things that we knew some constant approximation algorithm, but it seemed like there should be better ones. There were problems where we didn't have constant factors, and we really think there should be. And in general, I can tell you, quite famously, I have been on the losing side of many bets because I'm what I believe to be an optimist. That is, I believe there should be strong positive results, and the number, I won't even embarrass myself by saying things that I bet against that have been provably impossible. I continue to, or at least modulo P and NP, but I continue to be,
One of your optimists?
Okay, I'll tell you my most embarrassing one. Okay, so when Papadimitriou and Yannakakis published their Max SNP paper, I publicly said, and people out there can go back and it's a great result. It's a wonderful result. It unifies all of these problems because there's a scheme for all of them, and we just need to get them for one of them. Bounded degree vertex cover. Of course there's a scheme, Okay, I was wrong. But I'm an optimist, so that's just it's my nature. But anyway, as we were going through these open problems and trying to construct it, we were a bit distressed by the fact that we really couldn't put our hands on a problem that we really thought we could motivate people to care about in a fundamental way, where there was a constant known and there wasn't a scheme. And and it was still possible that there was a scheme. There wasn't an APX hardness result. So I know that there's a 2 approximation algorithm. I know that I can come within a factor of 2. But I don't have an APX hardness result. And so it's conceivable that for every possible epsilon that's positive, I can deliver you a polynomial time 1 plus epsilon approximation algorithm.
There are instances where the gap is even higher. Right?
Yeah, there are. Yeah. No. Could be.
Constant,
But for example.
Could have a scheme.
But for example, the problem I just talked about with release states is one where we have a log n approximation and there could be a scheme.
Okay, I see.
So yes, there's one example. In hindsight, had I been thinking about this problem 6 months ago, it might have made it to the top 10. So, but I would have had to convince David to do that probably because, we'll see. Anyway, but anyway, that sort of highlights 2 questions that aren't going to be resolved here, and I leave out there. For the preemptive version with release states, can we do a constant? Can we even do a scheme? And can we even do a scheme for this non-preemptive version where I'm going to show you a factor of 2, or at least outline main ideas. So I mean, Primal-Dual algorithms for covering problems is huge literature. In some sense, the birth of Primal-Dual approximation algorithms comes in covering kinds of settings in the work of Patel and Bar Yehuda and Evan. The generalized Steiner work, which was put into an LP context by Gomans and Williamson and vastly generalized, gave us really an injection of energy into this area that really started the modern history of Primal-Dual algorithms. And they've been expanding to a broader range of diverse applications over the last 20 years. Okay, time to get to work. As you've got the frame, let's start with a concrete problem. So I'm going to talk about the minimum covering knapsack problem. So what is that? I give you a set of items. Say the set is F. Each item I comes with a cost Ci and a value U sub I. Okay. We want to find a subset of items of minimum total cost that covers that demand. So I want that the sum of the UIs of the selected set should be at least D, and I want to do that at minimum cost. And I can set up the obvious trivial 0-1 integer program where I have a 0-1 variable of to include or not to include, and I get exactly that integer program. Okay? Now, basic philosophy. Is this a good integer program in terms of its LP relaxation? The answer is no, it's horrible. Okay, why not? It's horrible for even the most trivial of reasons. Let's say we have just 2 items. One has cost 1, one has cost 0. One gives me all that I need, the demand D, and one is just a little bit short, D minus 1. As an optimal integer solution, I'm stuck. I have to take the thing that has, the other one isn't enough. I'm not going to take both of them. So I'm just going to take the one that gives me my demand. It's going to have cost 1. Good. As far as fractions are concerned, I can take all of the second one. That satisfies almost all of my demand. I'm left with a 1 over dth fraction of my demand. I only have to take a 1 over dth fraction of that item. I only incur a 1 over dth fraction of that cost. And so the optimal LP solution has value 1 over d. And the ratio is then d. And by considering inputs with arbitrarily high demands, then I can make the integrality gap as big as I want. Okay, so life is bad as far as this integer program is concerned. So now let's make it stronger. Let's think about valid inequalities that I can add to zip up that formulation. And as I indicated earlier, these were proposed by Carr, Fleischer, Leung, and Phillips, building on similar work in so-called flow cover inequalities that came earlier of Padberg and Woolsey. So now what's the idea behind this? Suppose I think about one particular subset of my items, say subset A, and think about that I were set on including those in the knapsack. I'm going to use them to satisfy my demand. And then I'm going to have to satisfy the rest of the demand from everything else. So that I can express by this inequality, I'm going to let U of A just denote the sum of the capacities that each of the sum of the capacities of the elements in A satisfy. So the residual demand is D minus U of A. And so from the remaining items, I have to choose enough so as to satisfy that residual demand. So this gives me a way of, for every possible subset, generating one additional constraint. It also generates me no further strength to the integer program. So why am I doing, or linear programming relaxation? So why am I doing that? Well, here's the visualization of that. I put those three items in, and now I'm going to have to choose a subset from the remainder, and I only need to satisfy the residual demand. Well, now if I look at that item 6, I mean, it's unnaturally big. That it's in and of itself, it has way more capacity than itself. And as far as whether I affect the feasibility relative to any feasible solution for that, it would be sufficient to truncate its capacity back to just the remaining demand. It's only good for that subset A, but now that I've written out this exponential number of inequalities tailored for that subset, I can think about the effective capacity that that item brings to satisfying the residual demand. And I can express that in the following way, whereas I started out with an original capacity U sub I, I'm going to think about for that hand-tailored set A, I'm going to shrink it between U of I and the residual demand. And now I just need to satisfy that those residual capacities, those effective capacities, are sufficient to satisfy the residual demand. Okay? And that gives me a strength in inequality. If you go back to the example that I gave you before, it's not hard to see that that in fact means that I'm going to have all that integrality gap vanish. It'll just give me the optimal, the LP relaxation to this expanded linear program. Actually has an integer solution in that context. So I can even write this in a somewhat more compact way by realizing that the original inequality is just the same thing when I take the subset, the A being the empty set, that I just get back the original constraint that I started, so that I can think about my new strengthened LP as just being minimized the sum of the CIXIs, subject to the fact that the sum for any given subset A, the sum of the effective capacities that I've selected be at least the residual demand. Okay? So that's my strengthened linear program. And in fact, what Carr et al. Showed is that they could effectively come close enough to solving this and then round the fractional solution so as to obtain a solution that's no more than twice the optimal value from the fractional solution. And I'm going to do this now by devising a direct primal dual solution.
So if I took all of these exponentially many constraints and satisfied them sort of optimally, wouldn't I get the optimal integral solution? Or
No. I could get another fractional solution. And it's not hard to build examples for which there is some remaining integrality gap. There's still a gap. The one I showed you, yes, but no, not in general. Okay. I mean, that would be interesting. That would show that the separation problem is NP-hard. But as far as we know, it's open. Whether I mean, it's conceivable that the ability to generate one of those violated inequalities could be doable in polynomial time. Okay, so I'm going to use the primal dual approach. So if every primal there's a dual, this is the dual. We're going to have a dual variable for each constraint. The constraints corresponded to subsets A, so I'm going to have a dual variable V sub A. And I'm going to need to maximize this weighted average of the residual capacities, subject to the constraint that for each item, because the constraints in the dual correspond to the primal variables, so for each item, we need to constrain that the weighted sum of the effective capacities is at most CI, where I'm only adding over subsets that don't contain that element. Okay, and that's going to come up again. That just comes looking back in terms of what happens if you think about the effect of that you're only adding in those which aren't already in that subset A. Okay. Okay, so that's our dual. So I'm now going to give you the algorithm by example. And hopefully it'll be clear. And one point that I want to make in the course of going through this example is that, in effect, primal dual algorithms are nothing more than souped up greedy algorithms. Okay? That they are just greedy algorithms with a little extra zing to them. It's just a question of what you're greedy with respect to. Okay? So, all right, so here's an input. We have 5 items here. We are going to have a demand of 5 that we have to meet, and those are the costs and capacities that each of those items bring for our knapsack. Now, there are going to be 2 algorithmic invariants that or 1 algorithmic invariant that I'm going to maintain. I'm always going to maintain a feasible dual solution. And the dual problem is a maximization problem. The primal problem was a minimization problem. I'm going to keep increasing the cost or the value of my dual solution, and I'm gradually going to work to having a feasible primal solution. I'm going to start out with not taking anything. I haven't put anything to cover the knapsack, and I'm going to gradually increase the value, the dual value, until I terminate. Okay, so what's the easy way to get an initial dual solution? I'm going to set all the dual variables 0. Okay, and maybe I'll go flashback. That's the dual. And if you think about it, and of course it's natural to assume without loss of generality that all the costs are non-negative, because if there was a negative cost, I just use it and add it to my solution and move on from there. So I have non-negative costs, and I start out with my all 0 solution. Okay. I also start out with a set A that I'm going to maintain iteratively, and that's going to be my candidate solution as I build it. I'm going to start by having included nothing. I have a residual demand to meet of 5 because I haven't put anything in. And now I'm going to, in each iteration, I'm going to increase the dual variable corresponding to my current choice of the set A. Initially, that's the empty set. Okay, so I'm going to increase it. Well, how far am I going to increase it? Well, I'm going to increase it as far as I can without making the dual solution infeasible. So how do I think about that? Let's think about what our constraints were. Those were our dual constraints. And if I think about that, I'm only increasing 1 variable. So I'm increasing the variable corresponding where A is the empty set. And I want to know how far can I increase that dual variable without violating this inequality. Well, the only thing that's going to matter is the ratio between Ci and its coefficient, and that's going to limit how much I can increase. Okay? So, but the effective capacity of the empty set, the variable that I'm increasing coefficient, is just the real UIs, right? That those are the actual capacities that I bring. So I'm really just going to care about the ratio between the current cost of that item and its capacity. And I'm going to increase it as much as I can. That means I'm going to increase it up to the minimum of those guys. And what am I going to do once I've identified this? Well, that'll have highlighted a constraint that is now satisfied. If I increase that variable as much as that constraint will now be satisfied with equality. And I'm going to use that equality as justification for saying this item I, the one for which equality holds, I'm going to add it into my set. So I'm going to do exactly that. I'm going to set my dual variable up to 0.25, that ratio. And then I'm going to put that into my solution. Probably the colors don't show. It just turns slightly green. And I've added to my current set A the element 3. And I now have a residual. It has capacity 2, so the residual demand is now 3. And I'm ready to go on. But now let me make this point about greed. So which element did I add into the set? I added the element for which the cost per capacity it delivered was minimum. I gave you the one that had the most bang for the buck. At least step 1 seems kind of greedy. Okay, we'll see what happens as we go on from here. Okay, so as we go on from here, life becomes a little bit more complicated. I said I'm going to maintain the same kind of structure. I'm going to take the dual variable corresponding to my current set A, and that's the one variable I'm going to increase in a given iteration. So now I have to think about how much can I increase that dual variable without violating any constraint. Well, now I've started out, I've already put some mass onto the left-hand side of this constraint by some of the variables I've already been positive. So let me move that back over to the right-hand side. And that gives me the expression there. And those are my Ci tildes. And I've got an effective capacity. But what limits how much I can increase that one variable's increase is, yet again, it's not the ratio of Ci to Ui. Now it's going to be the ratio of Ci tilde to Ui tilde. So this is what's often called the marginal cost for that variable, for that item. And we're going to measure that greed with respect to the effective capacity given what I've already put in thus far, but I'm still giving you an explicit measure of how much cost per how much bang am I getting, or so how much buck per bang is it costing, and I'm doing the most cost-effective thing in terms of that ratio. And that's going to continue iteration by iteration. And generally speaking, whenever you have a primal dual algorithm lurking in there somewhere, the primal dual algorithm is nothing more than a greedy algorithm with respect to just the right notion of marginal cost per effectiveness. Okay? Michelle may disagree. Okay, so let's continue with the running of this algorithm. That was the minimum. I put that into the set. I now have 2 items. I still have a residual capacity of 1. And so I'm going to have to keep going. I'm going to increase another dual variable. I'm going to have to update my ratios. I'm going to choose a new minimum. That's going to determine which next item gets added. And so these are the 3 dual variables that I'm going to have made positive thus far. But now I add this additional unit of capacity. And lo and behold, I've actually satisfied all of my demand. In fact, I've oversatisfied the demand in terms of that last one put me 1 unit over. But that's fine. And that's my solution. I have nothing more to add, and I'm done. Okay? So I stop. So that's the whole algorithm. Yeah?
Sorry, can you explain the marginal cost again?
So the marginal cost here was that I want to figure out, as I'm increasing one dual variable, when does some constraint become tight? Okay? Now, in order to sort of figure out how much, I need to know how much slack there is in the system already. So I just take the original cost and I subtract off everything I've already put in, and that gives me how much slack I have. Now, one thing that you should not have trusted me on, but I'll come back and make explicit, is that, hey, I just made these constraints tight, and now I'm increasing more dual variables. How come I didn't violate the feasibility of all those other constraints I pushed to the limit before? And the key thing is here. The only sets that contribute to the leftover constraints are ones which sum over sets that don't have the element, and it now has the element, so I'm not going to actually increase any of it. So I'm no longer going to increase any of those dual variables, and so for all the dual variables that I will increase, they won't touch those constraints. They're lock solid. Okay? Everybody with me? Good. Okay, and this does, I delivered a reasonable cost solution, and it turns out the optimum is a little worse, but a little better, sorry. Okay, so here's in words to the algorithm that I just did by example. Just go through it just to set notation. We start with all the dual variables set to 0, and A is the empty set. We increase the dual variable V of A until it becomes tight for an item I. We add item I to the solution, and we repeat, and we stop once we've met our demand. Okay? And let's call our final solution S, and we'll just encode that by x sub I set to 1 whenever I is an S. Okay, I'm now going to prove, next 5 minutes, beginning in 10, nothing left on the floor, nothing hidden under the rug, the factor of 2 from beginning to end. Be trivial. Okay? So here's the analysis. Think about the last item that we added, the one that put us over the top. Okay, let's call that item L. Okay? Now notice that if we increased a dual variable V of A, L was not yet in A, because we would have only put it in once we actually added it to our cover. So if the dual variable is positive, then we know the corresponding subset is a subset of our output set without that last item. Now, we also kept going without that last item. So that meant that the total capacity of that set is less than our demand. Okay? But that means that if I subtract off any subset for which I have a positive dual variable and think about its total capacity, it must be strictly less than d minus u of a, that it's effective capacity. Okay? Good. So let's remind it. So that's the repeat of what I just did, just up there. And now I'm just going to analyze the cost of the solution, right? I mean, if I'm going to prove that this is a good algorithm, I have to show you that it produced a solution that doesn't cost too much. Okay? All right. So those are the elements I included. When did I decide to include an element? Well, I only included it when I made that constraint tight. And it stayed tight. So I know that I can substitute for Ci the left-hand side of that dual constraint. That's just writing that over. Now I can do the usual trick. I can change the order of summation. Okay? Here we're summing over all elements I and then summing over all subsets that don't contain I. I can instead sum over all subsets and sum over all I that are not in that subset, that are in that subset minus the subset A. Okay? So I'm now taking my dual variable for V of A, and I'm weighting it by the sum of the effective capacities of the elements beyond A that I included in my set. I can break those into two parts.
Wait.
Sure.
Sorry.
No.
Is this the capacity or the effective capacity?
This is the effective capacity because it's UI of A. Of A.
Good.
Okay? Okay? So now I can bust this sum into two parts. The part that was the last element and the part that wasn't the last element. Here's the last element. Here's everybody else. Actually, it's an upper bound on the everyone else because I'm now going from the effective capacity, which was the shrunken version, down to the true capacity. But it's an upper bound. Now, for each one of these, that's exactly what I knew. I only care about the summation when the V of A is positive, so I can upper bound this term by d minus U of A, the residual capacity of A. Furthermore, I can upper bound any effective capacity by d minus U of A because that's by definition. This is the minimum of its original capacity and the residual capacity of A. That's just the definition of what UL of A is. It's the minimum of UL and d minus.
Is it conceivable? Well, I guess you've got two inequalities here, but is it conceivable that those two things would saturate simultaneously or not?
It is conceivable. I mean, there are asymptotic. I mean, I can give you examples for which that is.
For which those two would set, but okay.
Okay, so now I have a bound. Let me make some space. Okay, but let me remind you what this expression is. It's just the dual objective function if I take out the 2. So I have a feasible solution and a V, and so I know that the value of any dual solution is less than or equal to the optimum. And I'm done. Okay? Proof complete. So theorem for the min-cost covering knapsack problem. If I add these knapsack cover inequalities, the Primal-Dual algorithm based on that can be used to derive to approximation. Okay? So that's the not so heavy lifting. I promise I won't prove from beginning to end any other theorems, but I'll give you lots of pieces along the way. Okay, so knapsack inequalities have really been shown to be useful in a variety of different contexts, and I give a number of references. And in particular, I want to highlight that this Bansal and Pruhs result that I already talked about had at its core, in terms of a rounding approach, again using these knapsack cover inequalities. They used a slightly different variant in a slightly different way, but still, at its essence, it was based on the knapsack cover inequalities as well. Okay, new problem, sort of, new problem. I'm back in a scheduling mode. I have one machine, and now I'm going to consider a relatively simple problem. Each job has a processing time, Pj. It has a deadline, Dj, and a wait, Wj. I want to choose a subset of jobs of least importance, minimum weight, that aren't going to make their deadlines. Okay? So now this problem is weakly NP hard.
So there's no arrival times for deadlines?
No arrival times, just deadlines. Okay? So it's all in the cost function. So this is a special case of the general problem that I gave. I just have a different cost function that looks like a step function, and different jobs have different height steps, but they're of that form. Okay? So it's a weakly NP-hard problem. It can be solved in pseudo-polynomial time. That it can be, there is a fully polynomial approximation scheme dating back 30 years, and then some, maybe 35 years. And And so in some sense, everything was known about it. There's sort of nothing new and interesting other than the fact that I'm going to show we can lift exactly what I just did to get an analogous result based on exactly the same kinds of inequalities. And it'll be a good stepping stone for where I want to go in terms of the min-sum general problem. So one thing to point out is that even in this context, if there are release states, there have been a lot of work on approximation algorithms. For one, if you consider the non-preemptive version, I said that that's already going to be something where it's hard to get any provable guarantee. In our usual sleight of hand, we can go from a minimization problem to a maximization problem. That rather than focus on minimizing the weight of the late jobs, I can maximize the weight of the on-time jobs, and all of a sudden life becomes much easier. That because it's easy to get a 1/nth fraction of the, there you just put one job in. And in general, so there was a beautiful Primal-Dual approach of Barnoy et al. That gave a 2 approximation algorithm for the maximum weight version of that problem. Or you can allow preemption and consider the results of Bansal and Pruhs. Okay, let me take a step back from this. What happens if all the deadlines were the same? Well, let's introducing some notation. Let P be the sum of the processing time. So I'm going to build a schedule from 0 up to capital P. Let's let capital D be the common deadline. So what is it that I'm doing? I'm going to have P minus D total weight of jobs that's going to come late. And really what I want to do then is I want to choose a subset of jobs that are at least weight P minus D of minimum total weight. So I'm really back with the same problem what was before, that if I think about the common deadline version, I really just have the min cost covering knapsack. So by going to arbitrary deadlines, I'm really in the same space, just one step up. Okay, so let me set the stage here. Let me assume, just for notational convenience, that for my n jobs, I've indexed them in order of increasing deadline. So one way I can think about it is that if I think about one particular deadline, if I think about how much work has deadlines earlier than that, I'm going to have to evict some of that processing to be late. How much of that work am I going to have to evict? Well, let's let P of I be the total amount of work that certainly has to complete by DI if it's going to meet its deadline. And so P minus DI of that has to be evicted to finish late amongst that subset. So I can build a constraint of this form that says that if I take the sum over all the jobs that have deadline less than or equal to I's deadline, and I think about the total weight of that, I have to select from that at least P minus DI. Okay? So this gives us an integer programming problem. If I go back to the case that all the deadlines are the same, it's exactly where we were a moment ago. So we can use exactly the same trick. We can take each of those inequalities and strengthen them knapsack covering style. And I just do that independently. For each possible item, for each possible deadline, I think about any arbitrary set of jobs that I'm going to commit myself to being late, that I'm already going to put into the set going beyond the deadline, and how much amongst the remaining additional things that I still have to go beyond that deadline am I going to select. And I'm going to have to select enough work, and I'm missing a primal variable here that should have been that I'm going to choose some binary selection amongst those jobs y sub j, and I'm going to, instead of adding up their true processing time, I'm going to measure their effective processing time, where I've shrunk the processing time relative to the residual demand. And that's going to generate a dual problem that looks much the same. Fortunately, this time I actually do have my dual variables. That we have a dual linear program of exactly the same kind of structure. Gets a little bit notationally more cluttered, but very much the same. Okay. Okay, that didn't move. Try again. And I'm going to design the algorithm in much the same way. So I took the old pseudocode, and now I just highlighted the differences by blue. So I'm going to start with all the dual variables 0, and I'm going to think about it as an empty set. I'm going to make a particular selection as to which dual variable to. I'm going to be a little bit more fussy. I'm going to think about the one with the largest residual demand, and I'm going to increase that dual variable until it becomes tight. Because I now have multiple of these D of A's. I have one for each of those items. So that's where the selection comes in. I'm going to add the item that's tight to my solution, and I'm going to repeat. And I'm just going to keep going until I have a schedule. The remaining jobs can be scheduled so that all meet their deadline. And that's something that we can check efficiently. We just essentially schedule the jobs in earliest due date order, and if there's a way of scheduling them all on time, that's got to be it. So I can check whether, having already made that amount late, that will be sufficient. But now, in some sense, the last job that I make late, intuitively, could be one that is a real processor hog. And now I've made it late, and things that I sort of were tentatively making late all along, it might have really been a bad idea. So I'm going to do what's now quite standard. I'm going to do a reverse delete, dating back to the Goodman-Williamson network design stuff. And I'm going to just think about, if I remove this job from the late set, could I then still schedule everything else? And if so, actually make it rejoin the on-time stuff. And in the end, the set that I'll output is the set L star. And those are the jobs that I'm going to do. So same philosophy, same structure. Same principles. OK, so I'm not going to do the analysis, but my goal in the next couple of minutes is I want to convince you that the analysis is just a souped-up version of exactly the same thing. Just have to I have to explain to you, why am I doing this reverse delete? And I hope to make that clear of technically where that is necessary. And once you understand that, everything else will sort of fall into place. Okay? So here's one key piece. Suppose the current iteration increases a dual variable v of Li. Okay? And think about the jobs that are put in the late set after that iteration. Okay? Possibly even in that iteration or later, and that stay in the undeleted set. Okay? So it stays as one of the jobs we're designated as being late. I claim that there is some job j in that set, so that if I delete that one job, the remaining set isn't feasible. And that's exactly what the reverse delete was making sure, that we really had a minimality property, and that's the formal minimality property that we needed. Okay? And so notice in the previous case, life was easy. That last job, L, satisfied that. That when I took that last job out, all of a sudden I violated feasibility. Now we have multiple sort of different constraints, and so we're going to have a more sophisticated structure, but that's the analogous statement of the lemma. Okay? Now, formally, in terms of the inequalities that I can draw, I'm going to end up with an inequality of this sort. And it's not so matter what really the indices of summation are. I have some subset of items that when I take out that job k and I add up its effective processing times, they end up being less than the demand. It ends up being infeasible. Okay? So that's the thing that falls out of that. And again, by the definition of the effective processing time, it's always going to be less than or equal to the residual demand for a given set. So you might remember in the analysis before, we sort of summed two pieces. This is going to be piece 1. This is going to be piece 2. Or this is going to be piece 1. This is going to be piece 2 in exactly the same way. And in particular, we're going to end up with the sum of some effective processing times is less than or equal to twice some dual variable. So I mean, I can run this, and I wish I could run it in fast motion, but I can't. But I sort of sped this up. So so that was the analysis that we did before, right? Those pieces came together, and we got twice the dual. Well, that's going to be exactly the analogous thing. We're going to do exactly the same trick. We're going to add up the weight of the jobs that I put into my late set. They were put in because the constraint became tight. I'm going to substitute its right-hand side. I'm going to switch the order of summation. I'm going to pull out those dual variables. I'm going to be left with this kind of summation. And that kind of summation is exactly what I had up on top. And that's going to be twice my right-hand sides. And that's going to be twice my optimum. And it just falls out in exactly the same way. So, this one? Where's this one? Yes, that should be an inequality. Thanks. Sorry. OK, and the resulting theorem is that these knapsack cover inequalities are strong enough for this setting as well. Okay. So now let's go up to the full scale, and I'm just going to give you a hint of what the formulation is and where the knapsack cover inequalities come here, and we'll call it a day. Okay, so general one-machine scheduling. This is the setting I talked about at the start. Each job has its own non-negative, non-decreasing cost function that's a function of when it completes. Let's assume for the moment that all of the processing, even more than for the moment, let's assume that all the processing times are integer. Okay? And the goal is to construct a minimum cost schedule. So I can set up an integer program in a so-called time-indexed integer programming manner. I'm going to introduce a binary variable x sub j(t) to mean that job j completes at time t. Okay? Now, one thing to take a step back is that I'm now introducing even a variable, and there are going to be constraints involved, for each possible completion time. So this is a pseudo-polynomial thing. It requires, as many variables in the value of the processing times, not in their binary encoding. And we'll need to deal with that, but we will. Okay, and what we're going to do, though, within the context of this very large formulation, is we're going to take the exact same thing. We're going to set up the natural integer program. It's actually going to be weak. And then we're going to strengthen it by the same kind of knapsack cover inequalities. And the two theorems that are going to come out of it are, on the one hand, if I deal with pseudo-polynomial time, and that I'll have a 2 approximation algorithm. On the other hand, I'll be able to compress the formulation to something that's polynomial and end up with a 2 plus epsilon approximation algorithm for any positive epsilon. And I'll give you yeah. I mean, but only, as much better. I mean, I can make it as close to 2 as you're willing to see fit in some sense in terms of the running time. Okay. So here's the formulation that I will base things upon. So again, I'm thinking about all the jobs that how much demand do I have to go that has to complete beyond time t. I know that there has to be the total processing time plus t minus t plus 1, if you think about the effect of the integrality, that much total work has to complete, effectively at t or later. Okay, that much work is going to incur charge at least f of t in some sense, again, using the non-decreasing aspect. And then I just have assignment constraints. Each job has to be assigned to finish at some time. Okay, so that's the natural generalization of that first bad integer program, and that's why I put it as a weak LP relaxation. And though in practice, once one gets to problems of this scale, it actually isn't such a bad relaxation, but that's neither here nor there. Instead, I'm going to do the same strengthening trick, sort of full scale. I'm going to take each of those d of t right-hand sides, and I'm going to then take an exponential number of each of them, by thinking about already making the set L to finish at that time or later. And now I'm just going to think about what additional work and measure only their effective processing times in terms of contributing towards their residual demand. So just the exact natural analog of the steps we did along the way. Okay. There's the primal, there's the dual. I'm not going to actually need any of those details. I just thought I'd put it up for good measure, but the only real point is it's exactly the same structure of everything we've been dealing with so far. And I'm not going to even go through the details of the variance of there, but again, I took the previous code and it's going to have to get souped up. We're going to have a little bit more. Again, we're going to have a selection criterion. We're going to think about which ones become tight. Might be some ties. I might need to do some special tie breaking. One needs to put some additional care in order to get the algorithm to something we can prove. We're going to do a reverse delete. That's going to be, again, a little bit more sophisticated, but again, it's exactly geared to get the same kind of criticality, minimality properties that we need in order to drive the analysis. In the end, I've got some tentative set of jobs that I'm going to think about setting on time, and I'll just schedule them in earliest due date order. Okay. And the theorem is that this leads to approximation algorithm. And I didn't tell you enough to, but I just want to give you a sense of, that's what comes out. Okay. What about this getting rid of the pseudo polynomial versus the 1 plus epsilon? I maintain this is really just standard at this point in terms of the kinds of tricks that are out there. For each job, J, think about the potential completion times. The integers, now I'm using the integrality assumption, the integers 1 up through P. Break them up into blocks so that within a block, that job's cost doesn't go up by more than a factor of 1 plus epsilon. Every time it goes up by a factor of 1 plus epsilon, then I'm going to start a new block. And now consider the intersection of all of those refinements. Just take the finest grained partition, and now I'm going to have a partition of the job so that the cost of any job stays within a factor of 1 plus epsilon within that block of finishing times. What I'm sliding a little bit under the rug is exactly your question about those FJs. The notion of what's the polynomial is going to depend on how, in some sense, how much a cost function should go up, and we're going to have to be able to specify that. But all natural, reasonable things work, and life is okay. So now I can consider an interval indexed integer programming formulation. I'm going to have a decision variable xjt that indicates whether job j is assigned to finish in the teeth block consecutively. And it's going to have to finish in one of them, and then I'm going to have to, again, think about how much work has to go beyond the completion of that. And by and large, with really minor complexity engineering going through, everything else remains the same. Yes. No. That would prove P equals NP, because amongst the special cases of this general framework is what I said, this weighted total tardiness time. So, and that I said was strongly NP hard, and we can expect to have a fully polynomial approximation scheme for something that's strongly NP hard.
So where do we see the super polynomial growth in epsilon?
The number of fibers would be given one over epsilon.
Right? Yeah.
The number of fibers.
Yeah.
Is exponential and 1 over epsilon.
Okay. So, and in some sense, working this level of generality, we actually can capture even more general models without sort of breaking a sweat. So things that people have considered are models in which machines can be non-available for a given time. That yes, whatever you're running can finish after the machine comes back up, but we have these sort of gaps where there, or even more generally, machines that run at variable speed. And you really there. And basically what happens is that these partitioned intervals just correspond to having that much capacity. And that's all that we really need in order to the framework to.
So this is a 2 plus epsilon approximation, right? So
correct.
Why is polynomial dependence on 1 over
Oh, you're
epsilon?
right. You're
Okay.
my bad. Yes. So yeah, it's conceivable that I don't need it. And now that I'm thinking about it, I was really kind of distressed, and I was sort of thinking about it. Where does? So I don't think there is any exponent. I think this dependence is just polynomial 1 over epsilon. So I retract that. So in terms of this construction, I think I just need 1 over because yeah. Let me take that offline, but I'm pretty sure. Yes.
Maybe you had a 1 plus epsilon or something that's. I don't remember, but maybe you had a 1 plus epsilon earlier for the minimum tardiness thing. So.
No, the point is that the only reason I couldn't have a polynomial 1 over epsilon is I can't have a scheme, but I don't have a scheme. I have 2 plus epsilon. So let me just move on. Okay, we'll take this offline at the end. And again, so that it lives to the primal dual theorem, that we can achieve a factor of 2 plus epsilon. So let me talk a bit about open problems. Well, I told you, I figured you'd be exhausted by now. So I actually front-loaded the first two we already talked a bit about. For the min-sum scheduling with release dates allowing preemption, I'd love to see a constant, or again, a scheme is possible. For the version I just gave, the 2 plus epsilon, there's no reason that there can't be 1 plus epsilon, but again, with an exponential dependence on the running time on 1 over epsilon. And it would be nice to see a result along those lines. Or prove me wrong yet again, give me an APX, give me an APX hardness result. Okay. The other thing that I've spent a lot of time thinking about is that these knapsack cover problems have a role to play in problems for which this capacity limit come up as sort of side constraints with other things. And sort of the prototypical example of a setting of that form, which is one of my top 10 open problems, is a so-called capacitated facility location problem, where we know that local search can deliver within a constant factor, and in some sense we have this general belief that there should be some math programming based approximation, but we don't have one. That we don't know of any, let's say for just concreteness sake, I know of no LP formulation for which there's a constant integrality gap. I have candidates, and they are in fact based on applying the analogous setting of the knapsack cover constraints in this setting. But I'd love to see a constant approximation algorithm along those lines. And then really my favorite problem, that all until now I've been talking about strengthening LPs by adding additional inequalities. But that's only half the story. The other real meta lesson of the last 25 years is getting the right LP formulation might also be thinking about in the right variable space. So we might want to move not to having exponential constraints, but having an exponential number of variables where each variable encodes a non-trivial piece of the solution. And the best example of success along those lines comes from a result dating back now really nearly 30 years of Carr and Carp for the bin packing problem, where they have variables that encode the packing of each bin. And they show a opt plus log squared. But there's no reason, and I would still conjecture, that that LP formulation is strong enough, and when I'm in a even as optimistic as I get mood, is no more than one more than the optimum. So really the ultimate approximation result, and you know, really please someone, I mean every year I spend at least a week thinking about it and I get nowhere. I know in this case, I think that there is no consensus opinion out there in terms of those people who've worked on it there. The last time I mentioned Christos, I was thinking about that. He says, "Oh, come on, that can't possibly be true." But I think it could possibly be true. So anyway, so that's some open problems. And one last shameless plug. And if you have any questions, I'd be happy to take them now, or just refer you to an excellent textbook. Okay, thank you.
Questions? Okay, so let me start with this one. So this idea of adding inequalities to linear programs. So you gave examples coming from Primal-Dual method, but one could also look at anything that the ellipsoid method looks at as adding new inequalities which are valid. Mm-hmm. So is there some sort of what's actually being done in practice? Are they looking at more inequalities coming from convex programming, or are they looking at the kinds of combinatorial inequalities that you're adding?
They're actually the strongest techniques in practice are inequalities that are defined themselves by the result of auxiliary optimization problems. So that are talked by, essentially liftings of combinations of existing inequalities that are in sort of the base formulation, and then showing a sort of auxiliary problem. They're so-called split threshold techniques. And there are a variety of different techniques that involve from these sort of lift and project kinds of methods. And that's really the biggest engine. It would be nice to prove something for those as well. That are based on the automatic, but given that we don't even understand how to do sort of the simple combinatorial things in a large measure, it's hard to know where to start.
So in particular here you had sort of an exhaustive list of inequalities which you could work with, but you work with a smaller subset of those. And is that the same framework for them, or is it really more like...
It's the same framework, except that exhaustive list is specified in an implicit way.
And is it finite for them? Or is
No.
No.
On the knapsack cover problem, do you have any
lower bound and the inequality gap?
It's 2.
2.
Don't ask me to give you an example. I'm not sure off the top of my head. But yeah. Yeah,
That
it's
seems quite plausible.
So for the standard packing variant of Knapsack, I think there is a recent paper that if you look at the laser relaxation and you look at the constant number of kind of steps in that hierarchy, then you get a 1 plus epsilon. For the,
it sounds nice.
integrality gap.
I don't know it. Sorry. I mean, it sounds nice. So this is less area, you say?
Yes. Okay, so the question would be whether it's also possible for the Knapsack cover.
I don't know of no reason why it wouldn't be, but
If you said at the beginning that there's no example where we know of a constant approximation and not a matching
no. I said quite to the contrary, that there wasn't, I said that in informing our list of, so what I did say that was closest to that statement was that in forming our top 10 list, there was nothing in that class that we were excited enough about that we could justify putting in our top 10. Today, I would argue for the problem I talked about today as being exactly of the mold, because I really think that figuring out, it might be something along, I mean, I could imagine something along the line that Thomas talked about in terms of this sort of hierarchy of things. I think something we'd sort of really make progress in a way that doesn't happen so often. That would be nice to yield a scheme for the scheduling problem I talked about. So yes, but there are examples out there. I wasn't trying to say that there weren't. It was just.
Okay, thanks.